Okay, so as always, we fill up the first row and the first column with 0. And now you will do the calculation for the rest. Okay, so anyone who finished this one? What value I have here? 3 diagonal. Very good. Okay. Excellent. Okay. So let's try the first row, and then I mean, if you have not done that, you can continue, right? So for the first one, it has a match, so it has to be diagonal for sure, right? And then it will be 1 plus the value of the previous cell in the diagonal direction, right? And then here is a different, so we look up and left. The bigger one, we go here, right? So only one direction, right? Again, here we have the match, so we have diagonal for sure and 1, right? Here we look up and left, so it has to be left and then 1, right? So far we only have one direction. All right, and let's, if you have not done that, you can continue at home, right? We have to move forward for the second pair, that is the data. Okay, So now we change this one to D. So this one we have data, and here we have data. Okay, and again we will work out the dynamic table here, and again see what we have. So again, 3 minutes would be enough for us to finish. Right? So again, here you see that we have data, data against data. Okay, so what did you have? Okay, you have 3 diagonal, right? Okay. How about John Juban? What do you have? Also, okay. How about Jared Martin? What do you have? Okay, excellent, right? Okay, so we have 3 and diagonal. Okay, so now let's work out, but this time I will work out with the column. Okay, column by column, right? So here we have G and D. So that said, we have to look for the left and the right, right? And then the bigger one will be the same, and we can go either left or up. So now we have two options, right? So go to the next. We have A and D. Again, we have 0, and we can go either left or up. Okay. And now again, we have T. We have the same thing. Okay. Yeah. A and D, same thing. Okay. So that said, we go column by column, right? So continuously, we will have the result that is 3 diagonal. Okay, very good. So the last one would be Gator against date. Okay. So I think I will show you the result. We don't have to practice anymore because it's very similar. But in this situation, we have the 2 instead of 3. Okay. So let's see what we have here for this 3 example. Yes. Okay, so here's what I have for this example. Okay, so here we have the Gator or Gata, and then against Gaga, right? So you have Gator, Gata against Gaga, right? So we have D3. Okay, very good. And now, and then here are the 2 options for the longest common subsequence. Okay, Gata against data. So here's what we have. Okay, so we have 3 diagonal, very good. And then again, we have 2 options. Yeah, 2 options. Now, Gata against date. So we have only 2, right? And then here are the different ways we can align there. Okay, so we have 1, 2, 3, and 4 different ways. Okay, so we have here 2, right? Now going back to this one, we know that Gaga and data give us 3, right? And the date give us only 2. So in fact, we can only offer the 2 different ways for the correction, that is Gaga and data for the Gata here, right? For the misspelled word. Okay? So that is the idea behind the algorithms for offering the replacement of, say, a wrong word. Now, the algorithm we learn is not the best. Okay? We need to make some changes for the algorithm in order to make it work. And the idea about what do we need to change for the longest common subsequence, we can run, actually they have a bunch of different ways to remember the previous calculation. But basically, when someone type in the wrong word, right, they will look up their databases and then find out that the longest common subsequence with the highest value is coming from Gaga and data with both 3. Okay, and then they offer that. Okay, do you mean Gaga, or do you mean data to replace the wrong one? But when we do our algorithm here, right, by filling up the dynamic programming table, we did not take into account some very important facts. What are they? You don't need to keep track of the direction. Yeah, correct, because we just want to know the highest value. Yes, okay. But another important thing is here. When we compare the two strings or the two words, we only use the fact that if there's a match, like A, we count it 1. If A is aligned with D, we say that it's 0 point, right? So in other words, we only count the subsequences that has the longest value or the longest characters that are matched, right? A and A. And then after that, we have A and A, right? Okay. So that means if we have a match of A with A from the string 1 and string 2, we count. But if they are different, we give it 0 value. And it's not very, very accurate. Okay? Now, here is the keyboard. Okay? What it tells you? If the first character is G, what does it mean? Okay, where's G? G is here. Right? Can you see it? Okay. So, if we have the first character of the first string is G, then we should give more score when we compare G with T, G with H, G with F, G with B, because it's highly likely that when someone type in instead of G, they press the wrong button, right? So that said, the key around G here should have more value than G when we compare with P, right? G when compared with P, there's nothing in common between them, right? They are far away. So in the first string, if you have G, in the second string, if you have P, then there's nothing in common. Say 0 value, right? But the first string has G and the second string has H. We should give it not 1, but something like 0.7 or 0.5, right? Okay, so you understand the idea? Yes or no? Okay, very good. So that said, we try to have some kind of scores based upon the design of the keyboard. Of course, here we have the keyboard in the United States. All of us are using that, right? So we know that how close a letter G on the keyboard to another keys around that one. And that is the idea of improving the LCS in order to make it work for making suggestion in Microsoft Word or on the website of Google. Okay, that is the basic idea behind their algorithms. In other words, we need to take into account the scores between two letters. If they are close on the keyboard, they have more value, not simply 0 for every mismatch. Yeah. So that is the idea, and here is what I incorporate that into my program, and you can see from here something like this. Okay, maybe I will choose a different thing. From this one. Okay, so here's one example. I have between the two strings, if the first one has A, the second one have A, I can give a score, something like, okay, 1, right? But I can also give it 3 if I pay more attention to the A. Okay? Here, actually, when we have the two genes and we compare them, right? Then if you have a match of the A nucleotide, we give it more score than if you have it something like, say, between A and C, right? So A and C, even though they are different, not a match, but we don't want to give it simply 0, okay? Because as I mentioned before, when on the keyboard, if they are close to each other, we can give it some scores, right? And depending on the distance from one key to the other, we can give it 1 or 2, okay? So like here, between C and T, we have 1. And in the same manner, between T and C, we have also 1. This one is a symmetric. So meaning that the score between C and T is 1, and it's also the score between T and C, okay, in the reverse order for every pairs. So that is what we want to do in order to improve our program that can give us a much more, say, realistic results when we talk about, say, misspelled word, right? So that said, we know about the LCS algorithm, right? But now we can improve it because depending on the real world problems we are working on, like spelling, right? We take into account whether or not we have the position of the key on the keyboard, right? Or for the gene, it really depends on how we have the matching of the genes in the real world. So in the real world, when we compare of the genes, then we have to done, actually biologists have done a lot of sequencing, and then based upon this probability they obtain, we have a table we call BLOSSOM, right? That BLOSSOM will tell us what is the score we should give for between the two nucleotides, like A and A, whether or not we give it more score than T and T. In fact, it is, right? So the BLOSSOM, we already have it from the biologists, and then we simply have the scores updated in our program. And in that situation, comparing the two genes, you give us a lot more sense in terms of the biological meanings. Okay? All right, so that said, we have done quite some hands-on exercises here. Okay, and then improving the code, right? So as I mentioned before, the LCS algorithm you learn is a generic algorithm, and we did not take into account some technical details like the problem for work replacement, or when we compare the genes. In that situation, we have to give different scores, even though if there is a mismatch between the two characters. Okay. Now, how do you feel? Do you still need some hands-on exercises? Okay, so you feel good for LCS. Okay, very good. So we don't need any more hands-on practice, right? Now, I can give you one more dynamic programming problem, or we can switch to the Bitcoins immediately. So I look at the programming contest training. Looks like you did the work for the matrix multiplication, but not for the Babylon Tower, nor the the chord change. Do we need one more problem in that we use dynamic programming? Jared and Caleb and John, have you tried the other two problems for dynamic programming on the website for ICPC for programming contest? Okay, so maybe I'll give you one more problem in that we design an algorithm for solving it. It has the exponential complexity, and then we try to solve the problem using the idea of dynamic programming, in that it takes something like n square or n cube, which is much better than the exponential, right? Okay, one more problem in that we use dynamic programming. So why don't we do this? Look at the problem, the Tower of Babylon that I posted. I think is the problem P6, right? Look at the problem first. Try to have a dynamic programming by yourself, and then I will explain to you how we can design an algorithm using dynamic programming for solving that problem first. Okay? So as I said before, for dynamic programming is the most important thing to identify, okay, how can we break the problem into smaller one, and say remembering the intermediate results instead of calling the recursive function again and again, right? So it's very important for formulating the idea. And it's similar to divide, concur, and recursive algorithm. We have many different ways to break the problem, and not all of them will work with dynamic programming. If you review the matrix multiplication, okay, the assembly line, and then the LCS, we all break the problem in different ways, right? And it's very important that in the real world, if you are given a problem to solve, you have to identify the way to apply the dynamic programming. So on Thursday, I will cover the solution for the Tower of Babylon, right? Since I will cover in the class, we don't need to have it today for the training. Okay, the training, in fact, will be on Thursday during the class time. Okay, so any question or any idea that you want to discuss? Okay, how about John? Okay, then I'll see you on Thursday, right? But don't forget to look at the problem P6 on the website, right? We will solve it, but it would be better to have some ideas before we really solve it using dynamic programming. Okay, and that's it for today. I think we are a little bit early. All right. Take care and bye-bye.